aerial satellite image of some moraines around Twin Glacier Lake. And you can see them beautifully picked out by the tree line. And these red dots here, those are sites that we visited and collected samples from. Now, they are really quite tricky to access, really dense rainforest infested with moose and bear, and particularly infested with mosquitoes, but really clear to see that imprint of the glacier. And then if we go onto the ice field itself, we can see where the surface of the ice field has lowered over time, because it reveals this really bright, clean, fresh rock. So we can say, okay, well, the ice elevation surface used to be here, and now it's come down to here. And we think the ice field occupied these moraines and was thicker on the ice surface in about the year 1770. And there were a few different surveys and hydrographic surveys and other pieces of information that make us quite confident in that. We're also very fortunate that in the 1948 and again in 1979, there was aerial survey of the ice field. So we have the 1948 aerial survey and then the high altitude aircraft program. And they took sequential aerial photographs across all of the ice field. We now have the tools and technology to do the world's hardest jigsaw puzzle and stitch all of these aerial photographs together. I've chosen a couple of quite attractive photographs here to show you, but quite a lot of the pictures are just white with a little bit of dark rock in. So you can imagine it's not an easy thing to do. And because they've been stored in a warehouse, some of them have got thumbprints on or are fixed with sellotape, or they've become a bit bent or folded. So it's a little bit tricky, but we now have the technology to automate the mosaic of photographs that can give us not only a picture of the ice field, but also a surface elevation model of the whole of the ice field in 1948 and again in 1979. And then in the 1970s, we also started launching satellites like the Landsat program. And you can see here the Landsat 1972 image, which looks quite red, compared with the Landsat 8 image from 2016. So you can see there's this massive improvement in the sensor technology on the satellites. The 1972 images aren't as clear as our aerial photographs, but by 2016 we're getting beautiful regular images of the ice field. And then we had the Sentinel Landsats launched in 2015, and they again take regular pictures of the ice field. So an example here of what it looks like, and you can see these beautiful glaciers and structures of the ice that enable us to reconstruct the glacier behavior all the way from the 1980s through to the present day. And what that means we can do is we can reconstruct the ice field's shrinkage and recession through time. So if you have a zoom in here on Mendenhall Glacier, which is right by the city of Juneau, and people live amongst the moraines here, we can see that the dark red is the ice field extent during that neoglaciation in the 1700s. And we go back through each time slice, and the white is the ice field extent in 2019. And we can reconstruct how much the ice field has receded in each time period. So just after that neoglaciation, it receded about 3.7 kilometers squared per annum. But by 2005, the ice field had lost 23 kilometers squared per annum. So every year losing 23 kilometers squared of ice across the whole of the ice field. And by 2015, that had increased to 45 kilometers squared per annum. So we can see this long-term acceleration in mass loss across the whole of the ice field. And because we can create these surface elevation models, we can calculate the thinning. And if we do a volume calculation, a density calculation, we can then calculate the volume of ice lost. So the three graphs here, they go from 1750 through to the present day. And the top is the change in area through time. We can see that's really starting to accelerate, that rate of change really accelerating after about 2005. Then that middle graph there, that is thinning per annum. And again, after about 2000, you can see the ice field is really starting to thin over the whole of the ice field. When we do a density calculation and convert to volume, we can see exactly how much mass has been lost. So quite low volume of total mass loss until the 1970s to about 2010, and then a big step up after 2010 with very significant amounts of ice loss. The icefield's now losing nearly 6 kilometers cubed of ice per year across the whole of the icefield. That equates to 5 billion tons of ice being lost every year. And to help you imagine how big that is, this is 1 billion tons of ice, 1 gigaton, over Manhattan. And this one icefield in Alaska is losing 5 of these every single year. And what are the drivers? Well, one of the drivers is the snow line is rising, and the snow line is now on that low slope plateau. So we can see on this map, you can see these black wiggly lines. That's the snow line in 2019, right up on that flat yellow plateau. And this is really important because it means that more of the icefield is exposed to net melt, and therefore less snow is remaining on the icefield through the summer. But it's also important because glacier ice is very dark. It's much darker than snow. Glaciers aren't white and shiny, they're actually quite dull. So it's absorbing a lot more of the solar energy and therefore melting faster. And because of this flat plateau, once the snow line reaches that plateau, you lose vast areas of snow very, very quickly. What we're also seeing is increasing fragmentation of the icefield. And you can see a picture here, an example of dark brown, black rock being exposed right in the middle of the glacier. And that's really important because it's very warm, this rock. Therefore, it absorbs solar energy, and that means it accelerates the melting of the ice. And I know it's warm because it's a good place to have your lunch, but it is not a good place to maintain your ice loss. So these valley glaciers, they're no longer getting nourished from the ice on the plateau, and therefore are losing mass. And this incidence of fragmentation, this is increasing through time because the snow line is now at the elevation of these ice falls around the edge of the plateau, where the ice is thin and crevassed and quite vulnerable to melt. And so once the ice field reaches them, it very quickly melts through to bare rock. What do we expect to happen in the future? If we model the mass balance of the ice field through to the next few decades, we expect to see almost all of that plateau darkening and having very little snow left. In this figure, this is the ice field and how it might look in 2060. This is just the mass balance. And the red areas are where we're losing mass, and the blue are where we're gaining mass. We should expect a good 2/3 of the ice field to be blue, but by 2060 it's almost all red because we're losing mass across all of the ice field. And the problem with Alaskan ice caps, ice fields like this, is that this is really hard to stop. If we imagine a situation where we have warming between T1 and T2, and then we stabilize that temperature gain between T2 and T3, your alpine mountain glacier may stabilize and remain. Whereas once you lower your flat plateau, even if you make the temperature the same and stabilize it, it will continue lowering. And it's very, very difficult to stop unless you make the climate a lot cooler. This is a picture of us skiing across the plateau, and you can see just how flat it is. There's nowhere for this ice field to go. So this is an irreversible once this process starts on any kind of human timescales. So I want to move on to my colleagues who are going to talk about some of the impacts, the societal relevance of this. But I want to highlight that this is part of a global acceleration of mass loss. We see this pattern of accelerating mass loss almost everywhere we look. But when we take this longer term perspective, we can really see the role that thresholds and feedbacks play in accelerating this mass loss. And if we continue, we're going to pass a tipping point, which makes the recession very, very hard to stop. Thank you very much.
Thank you, Bethan, for this very interesting presentation. We are now already moving on to the next speakers, and I'm very pleased to introduce Judith Dahutsu Ramos and Annika Ord. Judith is an anthropologist and assistant professor for Northwest Coast Arts at the University of Alaska Southeast. And Annika is a climate adaptation catalyst working to support climate adaptation and resilience initiatives in Southeast Alaska at the Alaska Climate Adaptation Science Center at the University of Alaska Fairbanks. And I want to thank both Judith and Annika especially for joining at this very early hour for them. And I'm now happy to hand over to you.
Yes, good morning. This is Judy Dahutsu from Yakutat. The Yakutat's the homeland of Mount St. Elias and the Malaspina and Hubbard glaciers. The first slide is a picture of Hubbard Glacier, the spirit of Hubbard Glacier, and the Mount St. Elias from the Yakutat area where I'm from. And this is a drawing by my daughter, Maka Matur. So can I have the next slide? So, can you?
1 second.
Sorry. Yes, so this is our land acknowledgement. We acknowledge that Annika and I are living and working on the traditional homeland of the Aquan people on Tlingit, also known as Juneau, Alaska. And Southeast Alaska is the homeland of the Tlingit, Haida, and Tsimshian people. We would also like to recognize and honor the Indigenous people of Brazil. Thank you. So next slide. So this is a map of the traditional Tlingit territory of Southeast Alaska. We are organized according to what is called Kwans, or people of different territories. So Tlingit people have lived and stewarded the coastal rainforest and waters of Southeast Alaska and Southwest Canada for at least 10,000 years. Oral history accounts different natural disasters, including the Great Flood. Our deep relationship stretches back for generations. It shaped our culture, identity, and harvest practices. Rapid deglaciation will disrupt our relationship between our communities and our connection to glaciers and glacier landscapes. It'll deprive our future generations of this component of our identity and history. Glaciers also served as natural glacier highways. My people migrated over the Bering Glacier from the Chitna River, Kappa River area, and ended up in the Icy Bay area, and then migrated down the Yakutat. There was also another story from the story of a Kwandan Chinchi man, or called Canadian Iceman. He died between 300 and 550 years ago, and he was found migrating back to the interior of Canada from the coast, and his naturally mummified body was found in the Tatachini-Elsac Provincial Park in British Columbia, Canada. So it shows evidence that for hundreds of years people were using the glaciers as highways. My people adopted to the tidewater in Yakutat, which is rich in resources like seals and berries, and birds were a very important resource. We also had to be knowledgeable about the wind currents and ice conditions when we were hunting in the ice. In my community, we adopted a special type of canoe called a gudia, which was a sort of icebreaker canoe. And on one end was an icebreaker, and the other end was a regular canoe. And that was used to push the ice out of the way when we're hunting in the ice. So next slide. So this is a photo of my father. He was the knowledge holder about the traditional hunting camps as the glacier receded from the mouth of Yakutat Bay. And he's pointing up towards Hubbard Glacier. So we have a very special, important relationship to glaciers in our land. Tlingit believed that everything in nature was alive and had a spirit. We call it a Kwani, and that refers to the indwelling spirit that was inhabited everything in nature. For example, Oz Kwani, or spirits of the trees, Teet Kwani, or spirits of the people in the waves. Glacier spirits have special spirits called Situ Kwani, and we believe that glaciers are gendered. They're male glaciers, that the ones that are advancing, and the female glaciers that are retreating. We felt they were sentient beings, willful and sometimes capricious, so we had to be very careful and quiet as we were approaching glaciers, and we had give offerings when we approached a glacier. So this is shows that we had belief that glaciers had their own spirit. Recently our landscapes are changing with the warming climate. One things that we're worried about are cedar trees, which are an important cultural resource, are not thriving in Southeast anymore. We're also seeing many unusual fish species showing up in our waters. And as the landscapes change, our Tlingit communities really expressing a deep sense of grief and loss because this will be affecting our culture and identity, which is inseparable from our land. So I'll turn it over to Annika.
Goodness, geez, Judy. Good morning, everybody. My name's Annika Ord. I'm also here in Zantikahini in Juneau, Alaska. I'm going to be talking a little bit about some of the impacts we see from that ice loss to communities today. Glaciers are really tied into the fabric of this landscape and often lie at the intersection between our terrestrial, marine, and human ecosystems. Here in Southeast Alaska, salmon are a really essential piece of people's identities, cultures, livelihoods. They're how we put food on our tables and feed our families in many ways. And this is especially true for the rural communities in our region, in Tlingit Ani. We're a region where communities are separated from each other by steep glaciated peaks and fjords in the ocean. And we don't have roads connecting us. So species like salmon are a really essential part of our cultures and our food security in the region. As you may know, glacier meltwater melts in seasons of drought or warmth, so in the summer typically, and that helps to cool downstream systems. And this cooling can have a really important effect during those periods of extreme heat waves that we're seeing more and more with climate change. And so they act as a buffer. Snow and ice in the mountain acts as a buffer to these climate warming impacts. And that's really important for salmon because salmon are really sensitive to those temperature changes. They are born and raised in these river systems, migrate out to the ocean to live, grow big, and then come back to the rivers to spawn. And so as we start to lose glacial inputs into these areas, we can expect to see some pretty big impacts on those watersheds themselves. And we're already seeing that in areas of southern British Columbia. In Southeast Alaska, we're a little bit more buffered because we still have pretty significant bodies of ice in the present day. But in the long-term timelines, we also kind of risk losing those important inputs of snow and ice. Another way that glaciers tie into the fabric of our community here in Juneau and across Southeast Alaska is through tourism. Juneau is a hotspot for tourism in Alaska. In 2023 alone, we hosted over 1.65 million tourists. And to put that in perspective, our community is only 30,000 people. So on some days, our population is doubled by tour ship passengers who are primarily coming off of cruise ships that pass through our region. And of those, of all the tourists that come to the state of Alaska, 1 in 3 come to the visitor center of the Mendenhall Glacier, which the Mendenhall flows right into the middle of our community, and is a really big component of our local identity. So as the Mendenhall's been retreating, it's slowly retreating kind of out of view, and it's expected to be fully out of view from the visitor center area by 2050. So that will certainly have an impact on our community. I also want to just highlight the really important kind of milestone that the Mendenhall Glacier Visitor Center in 2023, the U.S. Department of Agriculture entered an agreement with the Central Council of the Tlingit and Haida Indian Tribes of Alaska to co-steward this area. This is a really big deal. It formalizes an effort to protect historic and cultural resources here and to support Indigenous governance. Yeah.
Annika, sorry, excuse me for interrupting. We are not sure that we can actually see the current slides on the screen, and just want to make sure that they get advanced properly.
I advanced it on my screen.
Okay.
But I'll reshare.
We have glacier tourism now on the screen here. Is that
Yes.
the correct slide you're looking at? Okay.
That's the correct slide.
Perfect.
Yep.
Perfect.
Yep.
Just wanted to make
we
sure.
have just one
Sorry
more
again.
note on the co-stewardship, and then we're moving on.
Wonderful.
Yep.
Okay, thank you. Sorry.
Yeah, no problem. So yeah, this co-stewardship effort just really underscores the importance of local means of governance and supporting Indigenous sovereignty and stewardship of these lands and waters. The next piece I wanted to highlight before I pass it off to Donovan is Juneau's been experiencing these glacier lake outburst floods from a tributary, or what used to be a tributary of the Mendenhall Glacier, since 2011. And the vast majority of Juneau's population lives in the Mendenhall Valley below the Mendenhall Glacier.
I don't think that slide's showing, sorry.
Oh, it's not showing.
Oh, it's showing now, thank you.
Okay, I think things are just a little slow this morning. Yeah, so we've been seeing these outburst floods since 2011. They pass through the Mendenhall Lake into the Mendenhall River and have been flooding downstream areas. And this is pretty manageable up until 2023, when we started to see these record-breaking, unprecedented floods. In 2024, every year they've been getting bigger for the last 3 years. In 2024, we saw a flood that destroyed several homes and damaged nearly 300 homes. You can see a photo of those floods in the top right here. The city and borough in Juneau has installed a temporary levee to protect these homes from flooding. And it was fortunate to be successful this year. Although I will say that at the height of the flood, the levee was within inches of being overtopped. And this also isn't a long-term solution, so there's really this need to think about how to mitigate these impacts into the future. I think this outburst flood in Juneau is really a prime example of why it's so important that there's greater support for communities dealing with the challenges of climate change, and for communities who need greater support from our governments to help mitigate and manage these impacts. And so with that, I'll pass it over to Donovan, who's going to be talking about some of those governance challenges.
Thank you so much, Annika and Judith, and let's give them both a warm round of applause. And yes, then over to you, Donovan. And I quickly introduce you, sorry. So we are very pleased to have Donovan Dennis here. He's a project coordinator and scientist of the Tipping Points Model Intercomparison Project at the Potsdam-Institute for Climate Impact Research, as well as the Max Planck Institute of Geoanthropology. And he's now going to talk about governance challenges related to glacier loss. Over to you, Donovan.
Thanks, Julius. Just making sure that everyone can see my screen and can hear me. Yeah.
To both.
Okay. Yeah, so I would, first of all, thank you so much to Annika and Judy for their really important important overview on the impacts of glacier loss. Good afternoon to the room in Belém. Good afternoon to my colleagues around the world. Or good morning to the room in Belém. Good afternoon to my colleagues around the world watching online. And thanks to the ICCI, Amy, James, Julius, Pam, all the technical staff. And in particular, I'd like to thank and acknowledge all of those people in Belém, particularly those outside of the venue, on the opposite side of the fences from the negotiators, who've been raising their voices about the critical threat facing the Earth and all that lives on it. I'm going to talk a bit about the challenging governing space that tipping points in glacial systems are in, using the Juneau icefield as an example, as we've talked about already. This work builds off of a case study that we produced for the Global Tipping Points report on tipping in one of the icefield's outlet glaciers, Aktraksit, and also, which is also known as the Mendenhall Glacier. And as an outsider, compiling this information and placing it into a global context, it's only possible to do this because of the considerable work that's come before. Work by researchers based at the University of Alaska Southeast, and in assessments that have been drafted by the Tlingit and Haida Indian tribes of Alaska and the city and borough of Juneau, who have done incredible work and necessary and important work, as we've heard from Judy and Annika, on addressing the consequences of glacier loss in the region. We've heard already from Bethan about the challenges associated with anticipating glacier loss. We know that the icefield will continue to lose mass well into the future, this is another preliminary, or another modeling study that doesn't include necessarily tipping points feedbacks in it. And this delay in the observed impacts and the delay in the observed mass loss is particularly challenging in a governance sense, right? We know that even if we stop emitting CO2 tomorrow, we made rapid changes, the icefield glaciers will still take decades to respond. They're only now responding to carbon dioxide that was emitted in the past. And this isn't true just for Juneau icefield glaciers, but for mountain glaciers globally. This figure shows committed glacier mass loss at different global warming levels. The number in the center of the circle corresponds to the temperature at which 50% of glacier mass is lost. And we see that many of these numbers fall below current global warming levels, which means we've lost more than 50%, and that we will continue to observe these changes well into the future. The problem with this, of course, is that politicians who serve in elected offices and policymakers often think on much shorter timescales. So these are the lengths of time that some of the elected officials who are responsible for governing the area that includes the Juneau icefield, everyone from the US president to the mayor of the city and borough of Juneau. And the term lengths are often quite short, and even the amount of time that these people serve it pales in comparison when we think about the consequences of glacier loss and the impacts of glacier loss. So Lisa Murkowski, who is one of the longer serving senators, who served 10 years longer than the average, has still only been in office for 22 years. And when we contrast that with the governance timescale, or the governance timescale with the response timescale, it means that we have to consider governing today the consequences of the next century, the consequences of these GLOFs, the consequences for cultural impacts of glacier loss. And our governance systems and strategies will either have to stay on their toes or be adapted in order to anticipate the rapid and dynamically changing icefield. All of this can be complicated by the crossing of tipping points. And we know already, we don't need to tell our colleagues in Belém how hard it is to generate political will for long-term initiatives in governance. Some nations and jurisdictions have gotten around this challenge of democracy by defining legal safeguards for glaciers and other components of the landscape. So for example, in Tajikistan and Argentina, laws have been enacted to protect glaciers, particularly in light of their source, as a source of fresh water. In New Zealand, acknowledging the deep spiritual and cultural connection of the Maori people to the Wanganui River, New Zealand has recognized it as a living entity, an entity that can own property, sue, and be sued. and it must be represented in legal matters by guardians from the Maori and from the Crown. And in that sense, governance frameworks should and must learn from Indigenous ways of knowing. And at a minimum, an absolute minimum, that loss and damage frameworks should be expanded to include non-biogeophysical evaluations of glacier loss, such as cultural heritage. In Canada, youths have alleged and sued the government, alleging that the government has failed to protect their future, which includes failing to protect their cultural heritage in a case which has gained legal traction in courts there. In the absence of clearly defined rights for glaciers, governing the causes and consequences of loss means navigating a very complicated governance space, which has to anticipate change, not only the physical risk for people living near glaciers, but also how they live their lives and earn their incomes, as Annika and Judy so well described. Here are just a few of the different governance bodies that claim jurisdiction over areas that include the Juneau icefield only on the US-American side. This doesn't include the Canadian half of the icefield. So all of these actors, agencies have to work together over very long timescales to respond and anticipate change. We can then start to think about the ways that we can divide governance, right? So if we divide it into the causes, perhaps, and the consequences of glacier loss. The community of Juneau and the region of Southeast Alaska has virtually no meaningful means of legislating or influencing the causes of global warming. The state of Alaska contributes very little to global warming totally, less than 1% of the US's total emissions, though still more than many nations. But the United States has contributed more carbon dioxide historically than any other nation and remains one of the largest net polluters in the world. Meaningful climate action taken by the US could influence the outcome of glacier loss in Alaska, but instead, the US has notified the UN it will withdraw from the Paris Climate Agreement. This is in direct contrast with what we know about addressing the cause of glacier loss, which is that it can only be achieved through long-term, sustained international cooperation. Despite their capacity to govern very little of the cause, as we heard from Annika at the very end, governing the consequences of glacier loss, particularly in Southeast Alaska, falls almost exclusively on local and tribal governments. When it comes to the GLOFs mentioned, the city and borough of Juneau is the governing agency in issuing emergency notifications, deploying those flood barriers we heard about, and coordinating response strategies. The Council of Tlingit and Haida Indian tribes are providing emergency shelter. They're going door to door to make sure the community is safe. And the state of Alaska is coordinating the distribution of federal emergency funding. So all of these local actors are assisted by federal and state money, but they're the ones that are on the ground responding to this glacier change. And as deglaciation continues, we need to obviously support these governments and agencies in their decision-making, but we also need to then anticipate the very long-term challenges. This includes the potential expansion of extractive industries around the icefield, tensions between actors promoting mineral resource development in the region, and the emergence of salmon habitat have already emerged, right? We know that as the glaciers contract, more regions and more areas of the icefield that are currently covered by ice, but that are accessible for mineral extraction will be exposed. In Argentina, even laws enacted to protect glaciers are now under threat because of the desire to expand mining regionally. Furthermore, the icefield straddles the US-Canada border, right? So continued deglaciation thus stands to alter the accessibility and the border regions. While the US-Canada border won't likely be moving because of the way it's defined, recent examples from Italy and Switzerland have highlighted where the border moves because of watershed redefinition, as well as Argentina and Chile, and in Pakistan and India, where the movement of borders on glaciers has implications for transnational boundaries. So far, however, when it comes to thinking long-term, it's been the tribal governments of Alaska that have been at the forefront of providing the consistent governance in response to climate change. And their leadership should not only be acknowledged, but also supported by all other state, local, and federal actors. So I would then move to my last slide, the takeaway messages. And if I can leave everyone with one thing today, it's that the consequences of glacier loss play out over long timescales. I know Ricardo will talk about this. Intervention timelines are not aligned with impacts timelines, and that preventing glacier loss requires sustained long-term governance. And if that every 0.1 degrees C spent above 1.5 can reduce the length and magnitude of these consequences. So every action should be taken to reduce that overshoot. And with that, I'd like to thank everyone once more and to pass off to Ricardo.
Thank you very much, Donovan, for this very interesting presentations. For this interesting presentation, I meant to say. Yeah, and we are now coming to our last presentation in the session, and we are particularly pleased to have Ricardo Winkelmann here at COP in person. So, Ricardo, you can already come up to the stage. I quickly introduce her. Ricardo is a founding director of the Planck-Institute of Geoanthropology in Germany, as well as a professor of climate system analysis at the University of Potsdam and at the Potsdam-Institute of Climate Impact Research. She's also an IPCC lead author for the upcoming AR7 assessment cycle, and she will now be talking about tipping the cryosphere and committed impacts. And with that, I want to hand over to you, Ricardo.
Yeah, thank you very much, Julius. And I hope you can hear me. Can you give me a quick, yeah, perfect. And as we're setting up the slides here, let me start by just thanking also my fellow speakers from this panel. My fellow speakers from this panel. So we've now heard about the severe impacts that glacier loss has, both in the biophysical sense, but also on societies and especially on the local communities. And we've heard about the challenges that glacier loss poses when it comes to governance. And as Donovan just pointed out, one of the main reasons for these challenges are the timescales. So this clash of timescales between intervention times, so the time that's left to do something about this, and the response times of the glaciers themselves. And the same is true for the other parts of the cryosphere as well. And so I would like to focus on this point some more, and in particular bring this together with the thoughts on tipping dynamics in the cryosphere that we already heard about earlier. So this is about the long-term legacy of short-term climate action or inaction. And let me start by briefly introducing, well, what actually are tipping dynamics. So tipping dynamics are triggered when changes in part of a system become self-perpetuating because of positive or amplifying feedbacks beyond some critical threshold, which then lead to substantial, widespread, often abrupt and irreversible impacts. And I've highlighted a few of these points of the definition here because in the cryosphere, in particular in the ice sheets and in the mountain glaciers, we see that all of these attributes, all of these traits of tipping elements actually come to play. And I will very briefly walk you through those traits. So first off, we're dealing with a number of amplifying feedbacks. Here is a graph that relates to the ice sheets, but we have a similar graph for the mountain glaciers as well, where you can see that there are many of these feedback loops that can lead to an amplification. Let me give you just one example, which holds true for both the ice sheets as well as the mountain glaciers, and that's the so-called melt elevation feedback. We all know this from mountain climbing. If we hike from the top of a mountain to the glacier valley, then it gets warmer around us. And the same is true for the surface of an ice sheet, for instance. So if there's substantial melts at the surface and the surface is lowered, then that means that the temperatures at the surface are going to be higher, which can lead to more melt, which can lead to a further lowering of the surface elevation, and so on and so forth. So this, beyond some critical threshold, can really become a self-reinforcing or amplifying feedback. And as you can see, there's a number of these kinds of feedbacks related to ice sheets and glaciers and the other parts of the cryosphere. And it's really the balance of these amplifying and dampening feedbacks which determine the long-term stability of them. We also have multiple features that show that glaciers and ice sheets can change abruptly. And we know this from observations. So here, for instance, an observation from the Greenland ice sheet, where the Juneau glacier collapsed in parts. What you see here is a clip from a movie showing how over the course of just a bit more than an hour, several square kilometers of the Juneau glacier actually calved off. So you have to imagine this is similar to Manhattan basically collapsing in the span of more than an hour. So we know that abrupt change exists from observations, but we also know this from modeling as well as paleo evidence too. And we've recently put together a review specifically for the Antarctic ice sheet on the emerging evidence of abrupt changes in the Antarctic environment, not just for the ice sheet, but also for the surrounding ocean as well as ecosystems. And we're bringing together here the observed changes with the susceptibilities of different parts of the ice sheet and other parts of the Antarctic environment to basically collide a map of the hotspots when it comes to abrupt change. So we know that there are amplifying feedbacks and that there is abrupt change in the cryosphere. But most importantly, the changes that we bring about in the cryosphere through increasing greenhouse gas emissions and therefore global warming are also irreversible for the most part. And here's an example of simulations from the Antarctic ice sheet that show this very clearly. So we're basically slowly ramping up the global mean temperature here. And what you see in this animation is how there is a sequence of tipping points or critical thresholds, starting with a collapse of the Western Arctic ice sheet around 2 degrees of warming, which is mainly driven by ice-ocean interaction. And then as the temperature increases further, you can see a retreat of the marine basins also in East Antarctica. And then with even higher temperatures, you can see that the surface processes, similar to Greenland, become dominant as well. And this is where, over long time scales, the Antarctic ice sheet could eventually disintegrate. Now, these are, of course, very extreme scenarios, but you can see that even for low temperature levels, between 1 and 2 degrees of warming, the long-term consequences are already really severe, especially in the Western Arctic ice sheet. And we can also then use our models to run the reverse experiment. So after the retreat, after the warming, we can cool down the planet again in our models and observe what happens on this regrowth path. And as you can see, the two pathways differ substantially. So this is what in physics we call hysteresis behavior. That means that the ice volume between the warming and the cooling pathway can differ by as much as 20 meters sea level equivalent. And it also means that once some of the ice is lost, it would actually require temperatures well below present day levels to regrow that initial volume again. So these changes are really practically irreversible. And that is also why in the last summary report, the IPCC stated very clearly that the choices and actions implemented this decade will have impacts now and for thousands of years. And I think the ice sheets and the glaciers are a prime example for this. So these are the committed impacts, the lock-in effects, and we need to consider these different timescales when it comes to our decision-making also here at the COP in Belém. And with these time differences, we need to acknowledge that our decisions and actions now will have these long-term committed impacts, including the fact that it is virtually certain, independent of future warming, that global mean sea level will continue to rise over the 21st century, and that in the longer term, sea level is committed to rise for centuries to millennia, due to continued deep ocean warming and ice sheet melt, and will remain elevated for thousands of years. And what this means in terms of regional sea level rise are these risks shown here. So the risk of areas that are heavily populated today becoming inundated in the future over these long time scales. So just to sum up, we see in the cryosphere, in the glaciers and in the ice sheets in particular, that there is massive potential and a risk of kicking off amplifying feedbacks of abrupt change and of irreversible change. And that also means that we can kind of flip this question around, because it also means that our climate action right now has the potential to have really long-lasting consequences as well. For instance, it has been shown recently that climate action could save half of the world's vanishing glaciers if it occurs rapidly and decisively. And with that, let me leave you with this thought, because I think we can learn from the glaciers and the ice sheets that the question of climate action is really a question of justice, a question of international justice, as we heard earlier, but it's also in particular a question of intergenerational justice, because it's about these longer timescales. It's about the next generations, our children and our children's children, who will bear the brunt of the impacts from the changes we impose now. Thank you very much.
Wonderful. Yeah, thank you very much, Ricarda, for your presentation. Yes, indeed, we are now coming to the end of our session, and I want to thank very much all the presenters from the session. So, and thank you for your very interesting and indeed very important contributions here that really highlight the impacts from ice loss in the cryosphere, all the way from Alaska to the Arctic ice sheet, which is basically all around the world. And yeah, as I said, with that, we reached the end of our session this morning, and I thank you all very much for attending. And yeah, thank you.
Just popping in here to say thanks again to the organizers. I don't know if I hope I can't be heard in the room. But yeah, thanks to everyone. Thanks Annika and Judy, and yeah, it's really great to see you.
Thanks, Donovan. Thanks, everybody.
Thank you.
Yeah, have a good day, everyone.
For your contribution.